All right, let's continue with activity 6, and we're on question number 5. Predictor 8 is not significant in the multiple regression model, and it's asking us, would we be justified in dropping it from the model? Why or why not? Well, in this case, yes, we would be justified in dropping it from the model, because what the lack of significance is telling us, the p-value bigger than 5%, is it's telling us that once we have predictors 1 through 7 already in the model, adding predictor 8 to it does not significantly decrease the sum of squared errors. So if it doesn't significantly decrease the sum of squared errors, we don't need to add it to the model, and so we'd be justified in kicking it out. Now, unfortunately, we're not able to just look at the list of all the non-significant predictors and kick them all out simultaneously. That's because the p-values are model dependent. If we were to kick out predictor 8, then it could be the case that the p-values for predictor 6 and 7 change are now below 5%, meaning that we want to keep them in. So in order for us to determine whether or not we can get rid of a set of variables or whether or not a set of predictors is statistically significant, we need to perform a partial f-test. So there are 5 non-significant variables in the multiple regression model, which we see as predictors 1, 3, 6, 7, and 8, and we'd like to know, can they simultaneously be dropped? So how do we do this? Well, we're actually going to compare 2 models. We're going to fit the model without those predictors, and then we're going to fit the model with those predictors. And we're going to look to see, well, how much did adding those 5 predictors decrease the sum of squared errors? And if that decrease is significant, unlikely to have been produced just by chance, then we will say that the set is significant here. So I'm going to name a model m.simple to be the model just containing the significant predictors. So sales from predictor 2, predictor 4, and predictor 5. So I will fit this model. And then what I will do is I will fit the model with that set of predictors. And in this case, I'm just going to use the twiddle dot because including those predictors means everything is in that model that's in that data frame. So this is m complex. And what I'm going to do is run the ANOVA command. So m.simple, m.complex. And here is what I want to look at. So here is the sum of squared errors of the simple model, basically the model without those 5 predictors in it. And then here's the sum of squared errors with those 5 predictors. And we see a decrease, but that's not surprising. Adding more predictors into the model gives it more wiggle room to fit the data better. So we're always going to see a decrease when we add any set of 5 predictors, even if they're completely unrelated to y. So what is the p-value of the reduction? Right here, 11%. So what this is telling me is that adding those 5 predictors into the model does not statistically significantly decrease the sum of squared errors. I would expect to get this large of a reduction just by random chance if I added any sort of 5 random predictors to the model. So yes, those 5 predictors can simultaneously be dropped. It looks like that once we have predictors 2, 4, and 5 in the model, nothing else, no addition, is helping to improve that model. Adding in predictors 1, 3, 6, 7, and 8 does not improve our model anymore. Okay, so all of these p-values, all of the coefficients, all hinge on the multiple regression model being a good description of how the average value of y changes with each of the predictors. And so one of the key things is to always check the validity of our regression model. So to check the assumptions, we're going to use the command check regression, just like what we did for the simple linear regression. And I'm just going to copy and paste where I ran this model, just so that I make sure that it's defined again. And check regression, remember, is in library reg class, so I want to make sure to load that up. And let's see what this has to offer. Okay. So the first thing I look at are the statistical tests, because if I pass those, then I'm good to go. So for each predictor in the data set, I have a test for linearity. Now, previously in the scatter plot matrix, I looked at it and it seemed like the average value of y changed linearly with each predictor. And what I'm finding is that statistically that seems to be the case. I do have a few violations here, namely in predictors 4, 5, and 6, and that warrants further investigation with the predictor versus residuals plots. So I'll come back to that in a second. I do pass the test for equal spread, and I pass the test for normality, so I don't have to worry about that. Okay, so there's some hint of nonlinearity, specifically with predictors 4, 5, and 6, and I need to check to see, okay, well, is this amount of nonlinearity a deal breaker? So these plots right here that just appear by default, this is the residuals plot where we look for overall curvature or unequal vertical spread. It looks totally fine. I don't see any sort of hints of curvature at all. The QQ plot of the residuals and the histogram of the residuals just confirm that already what we know is that, yeah, it looks normal enough. When I move my mouse over here, click this area and click return, that's going to start giving me the predictor versus residuals plots. And the ones that I need to check are for predictors 4, 5, and 6 because that seemed to have questions. So I'll press enter a few times. Here's 4, here's 5, and finally here's 6. Okay, so I've failed the test for linearity here, but do I see anything that is a severe violation? Well, looking at this guy right here, I don't see anything at all. To the untrained eye, and maybe your eye picked up on this, you might say that, wait a second, do I see a little curvature going like this? Well, no, that's not going to be real, because remember my guideline, if you can mentally delete a few points and have that pattern go away, it's not really a real pattern. So if you were to kind of mentally delete this point and this point right here, I imagine that any sort of hint of curvature would go away. So no, there's no nonlinearity here. Whatever violation that test was picking up on must be pretty small and inconsequential. Likewise, for predictor 5 and predictor 6, I don't see any obvious signs of curvature. So whatever violations that are causing these tests to fail must be small enough for me to just be able to ignore them. So I would say that, yes, it looks like all the assumptions hold up. We have linearity with each predictor. We have equal vertical spread from that residuals plot, and we have normality from the histogram and QQ plot. Those statistical tests were actually passed. Okay, moving on, we want to examine the effect that correlation among the predictors have on our model. So previously what we saw was that predictors 5, 6, and 7, I believe, look to be fairly strongly associated. If I look back at the scatter plot matrix, that's one thing about check regression is you have, when you're done, if you don't want to see all the plots, you just click Q and press enter. Otherwise, I won't let you do anything else. So let's look at the scatter plot matrix. And we saw that, sure, yeah, predictors 5, 6, and 7 look like they have some pretty strong association going on. And what we know is that when there are associations going on between predictor variables, some of the information that those variables are giving about y may be redundant, and that actually makes estimating those coefficients relatively difficult. All right, so one way to tell whether or not correlation is affecting our estimates is to look at the variance inflation factor, the VIFs. So to get the VIFs of our model, not hard at all. It's just VIF on our model right here. And here are the numbers. So 1 means there's no correlation between it and the other variables. A larger number means that there is a substantial amount of correlation. Basically, the VIF is related to the R squared of the regression if I was predicting, say, predictor 7 from the rest of the predictors in the model. And a high VIF means that predictor 7 is actually pretty well predicted by those other variables. So we look at the VIFs of the predictors and we can ask ourselves, okay, well, how many times larger is the standard error of, say, predictor 6 compared to the case where all predictors were independent? So what the VIF is telling us is actually how much larger the standard error of our predictors are compared to the case where all the predictors were independent. So right now, predictor 6 has a standard error of 0.10. What that means is that my estimated coefficient of predictor 6 in this model is about 0.05, but we know that's not the truth. It's probably off from the truth by about a standard error or so. And it's saying that, okay, this estimate of 0.05 is probably off from the truth by about 0.1 or so. So predictor 6 has a VIF of essentially 6, and if I take the square root of that number, this is telling me how many times larger the standard error is compared to the case where all the predictors were independent. So essentially this 0.10 here is 2.5 times bigger than what the standard error would have been had all my predictors been independent. So yeah, that's a fairly large degradation in the precision of my estimates here. Okay, so do we have multicollinearity here? Are there problems with the amount of correlation? Are they really degrading my estimates? Well, the threshold for a large VIF is 1 over 1 minus r squared. So I'm going to do 1 over 1 minus the quantity r squared. And this is r squared, not adjusted r squared. So 0.6769. Let's see what this turns out to be. So our threshold is essentially 3.1. If we have a VIF bigger than 3.1, that means that the predictors are doing a better job at predicting that variable than they are at predicting y. So we see that we have 1, 2, 3 predictors whose VIFs exceed the threshold, and so multicollinearity is somewhat of a problem here. So predictors 5, 6, and 7 are probably contributing a bunch of redundant information to the problem. And looking back at predictors 5, 6, and 7, well, we see actually that predictor 5 was statistically significant, predictor 6 and predictor 7 was not. In the simple linear regressions, predictor 6 and predictor 7 were significant. So probably what's going on is that once predictor 5 is in the model, predictor 6 doesn't add anything new about the sales. Basically, the information contained in predictor 6 is redundant with the information in predictor 5. The same thing for predictor 7 there. Okay, well, we can get confidence intervals for the coefficients. We know what we estimated isn't equal to the truth, basically what the coefficients would be if we had all data on every product out there. So we know that the 95% confidence interval is about our estimate plus or minus about 2 standard errors. So we can use the command confidence interval to get 95% prediction intervals here. So we're 95% confident that the coefficient of predictor 3 is somewhere between minus 0.007 and 0.2. 0 is inside this interval, so 0 is a plausible value for the coefficient, implying that it is not a statistically significant predictor, the same information we got from its p-value. Okay, so we can make predictions from this model. We know our predictions aren't going to be exactly equal to the truth. There's some uncertainty associated with that, so we want to come up with either confidence or prediction intervals. So in this case, I want you to actually come up with 95% prediction intervals for new products with the following values for the predictors. So since we're predicting the properties of an individual product, that's why we're doing a 95% prediction interval. Confidence intervals are just for averages here. So prediction intervals. In order to make the predictions, I actually need to make a new data frame containing the values of the x's that I want to make my predictions at. So what I'm going to do is I'm going to make a data frame called toPredict. And the way the data frame works is that I need to tell it the name of each variable and then the values of each variable. So how do I do this? Well, I have 8 predictors in my model. And so I'm going to start off by saying predictor 1 equals, and then in this case I'm going to tell it the 2 values of predictor 1 that I want to be predicting at, 14 and 10. Then I'm going to move on to predictor 2, 15 and 18. And you see that this is actually going to be fairly tedious. So what I'm going to do, since R doesn't really care about spacing, is I'm going to start putting these guys on separate lines. It'll still read in just fine. And I'm going to copy and paste some stuff so I don't have to keep on typing everything out. So predictor 3, 4, 5, 6, 7, 8. And we had 15 and 14, 16 and 20, 15 and 11, 15 and 20, 15 and 23 and 14 and 15. So I don't need that last comma because nothing else is coming out after that. Once I close this right parenthesis, you'll see that it's closing off the data frame command. So when I run this command, I have my new data frame to predict, and we see that, yep, it contains 8 columns, and these are the numbers that I'm making my predictions at. One important thing to remember is that the names of your columns must match up exactly to the names of the variables in your data frame. So if you're typing this stuff out, you've got to make sure that's exact. In the homework, you're actually going to read in a separate file, so you don't have to do any of the typing. But okay, once we have the toPredict data frame defined, we can use the predict function, name of the model, new data equals toPredict, basically where we're making our predictions, and the interval is the prediction interval. This is either prediction or confidence, depending on if it's an individual's value or an average value. Since we're predicting individuals, it's going to be the prediction interval. So I can run this, and here we go. All right, so for that first product, our best guess is that the sales is going to be 15, and we're going to say there's a 95% chance that the sales are somewhere between 11.6 and 18.5. That second product, we predict the sales to be 14.9, just a little bit less, and we have a little bit more uncertainty associated with that, an interval that ranges from 10.9 to 18.9. So one thing that we'll talk about after the midterm is the reason why the intervals are of different widths. It reflects back on to why intervals are different for simple linear regressions. Basically, the farther away that we predict from the overall average of the x's in the data set, the more uncertainty that we have. This product, I guess, had a more representative cross-section of predictor variables than this guy right here. So we have relatively more certainty about where this prediction is going to fall than this guy, because this guy up here, the first product, is closer to the average. Okay, so that is all for Activity 6. Good luck with the homework.